The induction motor. How this essential machine powers our world. The electric motor stands as one of humanity's most pivotal inventions. It is the silent, ubiquitous workhorse of modern civilization, found everywhere from the pumps that deliver our drinking water to the elevators in our buildings, the cranes on construction sites, and even the cooling systems of nuclear power stations. In this detailed exploration, we will look inside one of the most common types of three-phase induction motor to understand precisely how it turns electrical energy into the mechanical force that drives our world. The outer shell. Form follows function. An induction motor typically has a robust cylindrical housing. At the front, a shaft protrudes. This is the output that rotates and connects to machinery like pumps, fans, or pulleys to perform work. At the rear, you'll find a fan covered by a protective grill. This fan is directly attached to the shaft, so whenever the motor runs, the fan spins. Its crucial job is thermal management. Induction motors generate significant heat during operation. The fan draws ambient air over the motor's casing, cooling it. Overheating is a grave danger, as it can melt the enamel insulation on the internal copper windings, leading to a short circuit and catastrophic motor failure. To enhance cooling, the casing features external fins, which increase the surface area for more efficient heat dissipation. Supporting the shaft at both ends are precision bearings housed within shields. They ensure smooth rotation while maintaining perfect shaft alignment. Inside the housing, the heart of the machine. Opening the housing reveals the two core components, the stator and the rotor. The stator, the stationary force. True to its name, the stator is fixed and does not move. It consists of a ring of laminated steel slots packed with coils made of insulated copper wire. Each wire is coated with a special enamel that prevents electricity from taking shortcuts between turns. This forces current to travel the entire length of the coil, which is essential for creating a strong electromagnetic field. In a three-phase motor, there are three separate sets of these coils, each physically spaced 120 degrees apart around the stator's interior. The ends of these coil sets are routed to an electrical terminal box on the motor's exterior. The rotor, the rotating core, mounted on the shaft inside the stator, is the rotor. The most common type is the squirrel cage rotor, named for its resemblance to a pet exercise wheel. It comprises copper or aluminum bars running along its length, short-circuited at both ends by conductive rings, forming a permanent closed-loop circuit. This cage is embedded within a stack of laminated steel sheets. These thin sheets, instead of a solid steel core, are vital for efficiency as they drastically reduce parasitic eddy currents. When the stator is energized, the rotor is what spins to deliver mechanical power. The magic of electromagnetism, the principle of operation. The motor's operation is a brilliant application of fundamental electromagnetic principles. A current creates a field. When electric current flows through a wire, it generates a circular magnetic field around it. Reverse the current, and the field reverses. A field can induce a current. Conversely, if a conductor like a loop of wire is placed within a changing magnetic field, a current is induced in it. Fields interact to create force. When the magnetic field around a current-carrying wire interacts with an external magnetic field, it produces a mechanical force, moving the wire, creating the spin, the rotating magnetic field. A single coil would only make the rotor twitch in a line. The genius of the three-phase induction motor is how it creates a rotating magnetic field. The three coil sets in the stator are connected to a three-phase AC power supply. In three-phase AC, the current in each phase reaches its peak at a slightly different moment, 120 degrees apart in time. When powered, each set of coils produces a magnetic field that pulsates in strength and reverses polarity. Because these three fields are spaced 120 degrees apart physically and are fed by currents 120 degrees apart in time, they combine to produce a magnetic field with a north and south pole that smoothly rotates around the inside of the stator like an invisible magnetic mirror, bringing the rotor to life. Induction and interaction. This rotating stator field cuts across the stationary conductive bars of the squirrel cage rotor. As per Faraday's law of induction, this relative motion induces a voltage, and because the bars are shorted at the ends, a large current flows through them. These currents immediately create their own magnetic fields around each rotor bar. Now, we have two magnetic fields, the rotating field from the stator and the induced field from the rotor. These fields interact. Opposite poles attract, and like poles repel. the rotor's magnetic field is constantly attracted to the moving stator field, causing the rotor to chase after it. Crucially, the rotor can never quite catch up to the synchronous speed of the stator field. This speed difference, called slip, is what allows current to be continuously induced in the rotor. If it ever matched speed, the induction would stop, and torque would drop to zero. The rotor bars are often slightly skewed, twisted along the rotor's length, which helps the rotation start smoothly and quietly, preventing magnetic locking or cogging. Terminal configurations. Star Y versus Delta Delta. The terminal box typically has 6 terminals, labeled U1, U2, V1, V2, and W1, W2, representing the start and end of each of the 3-phase windings. How these are connected defines a motor's operating characteristics for a given power supply. Star Y configuration. Here, one end of all 3 windings, U2, V2, W2 are joined together at a common star or neutral point. The 3-phase supply is connected to the other ends, U1, V1, W1. In this setup, each winding sees the phase voltage line to neutral, which is lower. Delta configuration. The windings are connected in 2 ends in a triangle. The supply is connected at each corner. Here, each winding is subjected to the full line voltage line to line, which is higher voltage, current, and application. The choice between star and delta has significant electrical implications. Consider a 400 volts, 3-phase supply. In delta, each winding gets the full 400 volts for a winding impedance of Vinci. The coil current is 20A 400V Vinci. The line current supplying the motor is higher at trace times. This are about 34.6A. In star, each winding sees a reduced voltage of 400 volts. Tresta Trio, the 5th, with the same Vinci. The coil current is only 11.5 A 230V Vinci, and the line current is also 11.5 A. Thus, the star configuration operates at a lower voltage and draws significantly less current. This makes star delta starting a common technique. The motor is started in the gentle star configuration to reduce inrush current and mechanical stress, then switch to the delta configuration for full torque, high power running. Conclusion. From its clever use of a rotating magnetic field and electromagnetic induction and a rugged squirrel cage rotor to the configurable windings that allow flexible starting and operation, the 3-phase induction motor is a masterpiece of electrical engineering. Its simplicity, reliability, and efficiency are why it remains the dominant choice for converting electrical energy into mechanical work, silently powering the infrastructure of our daily lives.